Hello everyone, our new chapter is thermodynamics. So we'll start with the first law of thermodynamics. In this chapter, I'll be mentioning about these different statements that the first law of thermodynamics has, and then the mathematical forms of first law of thermodynamics, the concept of internal energy that was introduced by the first law of thermodynamics, and some of its limitations. The first law of thermodynamics is identical to the law of conservation of energy, and it was put forward by Robert Mayer, Helmholtz, Maxwell, and Joule. The principle of conservation of energy can be stated as energy can neither be created nor destroyed, but it can be changed from one form to another form. There has been different attempts that have been made to disapprove this principle by constructing a machine which may continue to operate without consumption of any fuel and thus create energy out of nothing. In other terms, we call it as a perpetual motion machine. However, all such attempts have failed, and the net result is that the principle of conservation of energy has been universally accepted as a basic law of nature. We also call it as the first law of thermodynamics. So the different statements that you see on the screen. So the first statement, which says that there is an exact equivalence between the amount of work overcome and the heat generated, or in other words, we can say that the quantity of work is always approximately equal to the quantity of heat generated. Second statement, we can also say that the isolated system has always constant energy. That means the energy of an isolated system must always remain constant, although energy that we are saying, it can also convert from one form to another form. For example, the coal that is used in the train, that coal actually generates steam, and that steam gives a mechanical push by which the train moves in one direction. So there is a disappearance of one form of energy and it appears in the another form of an equivalent quantity of energy. Also, there is a fourth statement which says that no machine can work without energy consumption. That means it's not possible to construct a machine or a perpetual motion machine that could produce work without consuming any energy, because we always require energy to do some work or to get some mechanical work done. The fifth statement mentions that the total energy of the universe is constant. So, irrespective of the different statements that we have mentioned here, the first law of thermodynamics, all of these statements come to the same conclusion, that is the law of conservation of energy. That is, the energy of the system or the total energy of the system is always conserved. Now let's see what's the mathematical form of the first law of thermodynamics. Suppose some quantity of heat Q. So this Q is a quantity of heat is supplied to a system capable of doing external work. Then the quantity of the heat that is absorbed by the system is equal to the sum of the increase in the internal energy, that is represented by E, and the external work done by the system. So this is the external work done by the system, this is the internal energy which gets increased due to the rise in temperature. This is always equal to the amount of heat supplied to the system. So this is basically the mathematical form of the first law of thermodynamics. Now, if we try to put it more in a more accurate form, so what we can say is, in case of first law of thermodynamics, the heat that is absorbed by the system is always equal to the increase in internal energy, that is represented by E, plus the work done by the system, and that is represented by W. The increase in the internal energy of the system can be calculated. So if I try to calculate what is the amount of the increase in the internal energy of the system, this E is always equal to, so suppose if the system goes from state A to state B, so these are different states of the system, so it's moving from state A to state B. In that case, the difference in the amount of the internal energy, that is delta E, is going to be equal to the difference between EB minus EA. EA and EB are the internal energies associated with the system at the states A and states B. So there is EA is the internal energy associated with state A in the system, and EB is the internal energy associated with the system in state B. In order to do some external work W by the system on its surrounding, we can say that the amount of heat absorbed by the system is equal to the increase in the internal energy plus the work done by the system. So this work done is always equal to P delta V, that is the pressure and the change in the volume of the system. So in simpler forms, we can write that this Q here, that's the total heat provided to the system, is always equal to internal energy, that is the change in the internal energy, this delta E, plus the work done, that is W. Or in another form, we can also write the same equation as delta E plus P delta V, because W is always equal to P delta V. Or in simpler forms, if we have to calculate the change in the internal energy, we can write that delta E is always equal to Q minus W, or in other words, delta E is always equal to Q minus P delta V. So these different forms, they all become the mathematical form of the first law of thermodynamics. It's also important to remember from this mathematical form of the first law of thermodynamics that whenever the heat is absorbed, at that point of time Q is positive, and when this heat is evolved or liberated, at that point of time Q is always negative. The first law of thermodynamics, from the mathematical form, as you can see, it introduces the concept of the internal energy. So in our next section, we will see what this internal energy is and how the system attains the internal energy. The first law of thermodynamics introduced the concept of internal energy, which depends upon the state of the system and not upon how the system attains the state. Now, the internal energy of a system is an energy possessed by the system due to molecular motion and molecular configuration. The molecular motion is also called as the translatory motion. The energy due to molecular motion, that's the translatory motion, is called as the internal kinetic energy. So this molecular motion will be represented by kinetic energy. We call it as the internal kinetic energy, and this will denote by U with a subscript K. And the energy that is possessed by the system due to molecular configuration is basically the potential energy, and we will represent it by UP. The total internal energy of the system, that is represented by E, this is the total internal energy, is always the sum of the kinetic energy and the potential energy. But in our case, we are representing it by UK and UP by the molecular motion and the molecular configuration. That is, the internal energy is always equal to UK plus UP, or the kinetic energy, or the sum of kinetic energy and potential energy. The kinetic energy itself is a function of temperature. So this kinetic energy itself, it's a function of temperature. So that means the higher the temperature, the greater the kinetic energy, or kinetic energy is proportional to the temperature. So the greater the temperature, the greater the kinetic energy. The lesser the temperature, the lesser the kinetic energy. Now if we try to look at the change in the internal energy that happens from state A to state B, for example, then, or from the, we can call it as from the reactants to the product side also. So we can represent it by P, and this is by reactants by R and the products by P. So in that case, what happens is the change in the internal energy of the system is the difference in the internal energies of the products and the internal energies involved in the reactants itself. Okay, so we can say that the change in the internal energy, that is delta E, is always equal to the difference of the change in the internal energy of the products and the reactants, where P and R are the products and the reactants. So now this delta E is always going to be positive if this EP is greater than ER. Two cases. So if this delta E is positive, and when the delta E, that's a change in the internal energy, is negative. So this is going to be positive when EP is always greater than ER. That's the internal energy of the products is greater than the internal energy of the reactants, and it's going to be negative when the internal energy of the products is less than the internal energy of the reactants. The internal energy of the system changes when the heat is transferred from the system to surroundings or from surroundings to the system. So these are surroundings and this is the system. So the internal energy of the system changes when the heat is transferred from the system to the surroundings or from surroundings to the system, and this change can be determined by carrying the reaction at a constant temperature. So if I try to carry out this reaction in a system at a constant temperature and pressure, only then I will be able to determine the change in the internal energy. So there's a condition. In case of ideal gases, we have two different types of gases. One is the ideal gas and the other one is the real gas. So ideal gases are usually the hypothetical gases, and the real gases are the ones which we deal with in our day-to-day life. So in case of ideal gas, the intermolecular forces are always zero. So the intermolecular forces are always zero. That means the potential, that is UP, potential energy, is always zero. In other words, the change in this internal energy, that is delta E, that we have shown here, is the sum of UK and UP. In that case, what happens is, now since in case of ideal gas the intermolecular forces are zero, therefore this UP becomes equal to zero. That means the change in the internal energy is only equal to the kinetic energy. So in this case, this change, that is change in the internal energy, is going to be equal to UK only, because UP itself is zero. However, in case of real gas, what happens is the intermolecular forces are not zero. So the intermolecular forces are not zero. In that case, the delta E is going to be equal to the sum of UK plus UP, both of them. So this here is for the real gas actually, and whenever in case of ideal gas this UP is always zero, that means the internal energy always equal to UK. Now moving towards the limitations of the first law of thermodynamics, or the law of conservation of energy, it never gives us an indication about the direction in which the change can occur. So we know that the change is happening, but we don't know the direction of the change. It also does not give us information about the source of heat, that is whether the source of heat is hot or it is a cold body. In a similar manner, the first law of thermodynamics gives us no idea about the extent of the change. So it does not give us the direction of the change, it also does not give us the extent of the change, and therefore is silent about the question that why the heat engine cannot convert all of the energy into the mechanical energy, and why is some of the energy lost. These are the major important limitations of the first law of thermodynamics. I think this pretty much concludes my lecture for the first law of thermodynamics. I hope that you liked this lecture, and if you did like this lecture, then please subscribe to our channel and like this video.